So today we'll be looking at how to use a 1D battery model to plot an average electrode state of charge and also to plot the boundary electric potential with respect to ground in lithium-ion battery. So I'll be taking you through the step-by-step process on how to make this model. So we begin by moving to our model wizard, where we select our model wizard, which brings us to our select space dimension. Then, since we'll be dealing with 1D, we select 1D. Then we choose our model physics, we add our physics. So we select electrochemistry, it gives us our battery interfaces, and we add lithium-ion battery. So once it has been added to our physics, move to our steady, and we select the steady that we'll be dealing with. So we choose a time-dependent initialization. Once we choose time-dependent initialization, then we click on done. So we move ahead to add our geometry, our parameters, and we load it from our file. Console. We choose a 1D parameters and we add to we load to our parameters, as you can see over here. So we're able to see all the parameters that we'll be working with over here. See all our parameters. So after adding our parameters, we move to the geometry and we start to build our model. We specify add an interval where we specify interval lengths to add an interval length, then into input from our parameters, the variables from our parameters. This is LNEG, this is separator, that below is a positive. We build selected. So as you can see, based on these variables from our parameters, we've been able to form our geometry over here. From here, we move to global definitions, add functions, which will be interpolation, and the data source will load from a file, which will actually browse and load it. So select this, it becomes interpolation, and we import. So we import, we have PS over here, as you can see. So here we decide to change the name to EEQ. this and decide to make here cubic spine. Here is function. We plot to see how it looks like. So after plotting it, this is how it should appear. So when you plot and it looks different, that means you've actually loaded a different file. We'll go ahead to name the function. The units. So the unit appears over here, as you can see. Move on to add another function known as the piecewise. So with the piecewise to reload, which is the load cycle, so after loading the piecewise, you decide to plot and see how it looks. When we plot, this is how it should look like. See the start and function. So we change here to constant. Here we change to continuous second derivative. Make it 10. Absolute size. And you see how it goes. Move to make the argument s function is 1. Go ahead to plot, and this is how it should look. We change the argument at the top to be t, which we plot, so it becomes this way. We move on to add variables, which we will define as variables for the positive, current, letter, which will select a boundary at the end. We decide to name it I up PW 1 2 times I underscore 1 C over here, which we will describe as the applied battery cell current. Density. Move ahead to add materials from our library. Where we select the materials that you will be using. So we choose batteries, choose electrodes, and we choose dealing with this. So we select this for our battery. That's one electrode that we'll be using. We highlight the domain which should represent. So this represents this. When we open, equilibrium interpolation, and we plot. This is how it should look like. This is how the plot should look like. So we go on to add electrolytes. And also we have to select the domain. So we select all. Look at the interpolation and plot, and this is how it looks like for the electrolyte. So after adding our electrode and our electrolytes, we close this material section, and we go on to check our equations. So we see different types of equations over here, which represents output in the battery. So we want to show more and show more options. Equation view, advanced, click on OK. Come to our dependent variables. See our discretization, our charge balance bundle. Then we add porous electrode. Which we have to select the domain for that. So we just select here and we select our porous electrode. Go and we select, we check all necessary areas we have to define. You actually look at the electrode material and look at the electrical conductivity, which you will have to select. user defined. We'll name it as KSN. So we've named our electrical conductivity as KS underscore NEG, neg, because we chose this negative electrode side, and that's where the porous electrode is. Move to the particle. Move to the porous matrix. Name all integer. From here, the volume fraction, electrode volume fraction, and the electrolyte volume fraction. So name them as EPSS neg and EPSL neg. Move to effective transport parameter correction. Choose the electrolyte conductivity as user defined. And input this. Also come to the electrolyte conductivity where we choose no correction. Move to diffusion, choose user defined. We input the same. So electrolyte conductivity is user defined. Input this. Electrical conductivity, no correction. Diffusion is user defined, and correction factor. Input this. We move to porous electrode again. We expand. We look at other areas like the particle interpolation. Over here, we check the species settings, the particle transport. Change here to CS underscore neg. Change maximum species to user defined. Yeah, so it's a small caps C. We move to particle transport, where the interpolation, choose user defined DS particle mean center. Select this. The particle mean center surface distance. Check the operational SOCs for initial charge distribution. We select user defined. Also maximum electrode state of charge, select user defined. So we move to the porous electrode reaction as well. Check equilibrium potential. User defined. Which will define over here as EE. Unique. CS underscores surface CS max underscore unique. Okay, so like this. This is how it's supposed to be. Reference exchange current density to as well exchange to this. Temperature user defined for the temperature derivative of equilibrium potential. Remove and add another porous electrode. So we select the domain 3. We go down. Further, we check materials. Okay, overridden. Okay, so this has been selected as as 3, and this is still not selected yet. By the time we are done, electrolyte is for all the 3. This has been labeled. We move to porous electrode 2, and we define. So we move to the electrode properties as we did for porous electrode 1. Change the electrical conductivity to be user defined. Also, we select the electrode material, we move to electrode volume fraction, which we define as EPS positive, SL positive. So from there, we move to the effective transport intercorrection to be user defined, correction factor positive, we move to the electrolyte conductivity set as user defined, then EPS plus also diffusion to as well user defined. Is how actually EPS of the correction factor as well. We move to the particle interpolation. Where we first change to this, the particle material. This as well changes to this. So positive. So that's for the initial species concentration. And we have the maximum species concentration B from the material. Move down to interpolation diffusivity. It should be user defined as this. Particle mean defined as this. Then move to particle discretization, where the element order will be an order of 2. At particle discretization. Move to the porous electrode reaction view. Select the material. Select the reference exchange current density. Define it. we add we go on to add an electric ground, go on to add current density, so we move to initial values and we change the electrolyte salt concentration. Move to default inputs and we change this to T. Go to our time dependent and change to 10, 8,000. Move to our steady, define where it will be. So this side becomes our electric ground. And since we've added our current density, define where our current density will be, which is minus A applied. So with everything well checked, everything properly labeled, check our interpolation, no mistake anywhere. You can go ahead and compute. And this is the plot that we get after computing. So you're able to plot the electric potential against the potential V. And this shows the average state of charge from 0 to 8,000. So we see the electric potential against it for a period of time. That's the graph of the electric potential. So we label the title properly. And so that this comes here. Change this to cell voltage. As you can see here, move down. The position should be at the lower right. As you can see, boundary. We check our point graph. So we move on to duplicate this point graph one. See, and we click this plot on secondary y-axis. As you can see over here, we will make some changes in this point graph too. I'm going to change the expression to I app clicking here will show you where the expression we're going to highlight. Go to definitions, go to variables. That's it over here, as you can see. If you double click on that, it will actually give you IAP. So let's go on to plot it in it, and as you can see, it's been plotted together with the previous graph. So we go down to show legends, add manual legends to it. Then we name this as current you can see it has been updated on our graph. Select, make a selection as well. Go to point graph one. Just already be defined. We need to also show legends. So we go on and add a plot group. 1D plot. Go on and add a 1D plot, as you can see over here. Select the solution as none. So after adding a one plot group, we actually duplicate this. Takes us to data sets where we choose. No, we actually add a line graph. So we delete this instead. So we add a line graph to this where we select steady solution one. We choose from the lists. We select the 10 value, and we select all domains over here. We come here to change the expression to 0 plus 0.148. Show the legends, choose manual, which is 0 plus 0.148. Yes. So we duplicate this. And we change the expression to eta underscore 1. This can be found lithium-ion batteries, electrode kinetics. So as you can see, we can find this over here. So we change the legends to eta. As you can see. So we go ahead to add duplicates of line 1, which will eventually become line 3. So from our list, we select value of 1990 from our list. Then we input here as 0.558. This goes out. This comes 0.558. Eventually, the plots updates as well. So we move to next, which is 1D plot 6. We add, go to plot settings, y-axis, x. The y-axis becomes of voltage V. So when we plot it, it automatically updates as well as this. We move to this, we see it's this graph. You also select from list. You choose 1200 from this list. Then move along to choose, select again 1008. Move along to select 2200. Along to select 3000. Move down, then we select show legends, make sure it's showed button, then we plot. So when we plot, we have this electrolyte salt concentration graphs. Just to show the legend for all the times. Shows us all the time as coordinates and the electrolyte salt concentration. Move to plot settings, where select here as X and here as light concentration CL. A plot update. Here are the 1D plots. Where we select a time selection from the list. We select 10. We select 1200. We select 1800. Sorry, 10. Sorry, 10. Move to 1200. Move to 1800. Move ahead to the title where it will be manual. Select this as manual. Select this. Okay. Custom now. Custom. Make it black. Default. Select the title as electrode particle lithium concentration surface solid and center dashed just like this, and this. Okay, so the plot settings too as well. X axis will be X, Y axis will be CS, mole, and mole, sub 3, sub that way. We add a line graph to plot group 7. To be manual, we choose all domains. We select the entire domains over here for us. We choose the expression over here, which will go to lithium ion battery, go to particle interpolation. We go to particle insertion. We move to particle insertion. concentration. This one just after the solid phase concentration. So we select this, it appears, or we can actually just input this expression over there. It will show. So we move to show legends. Over here. Then we go ahead to duplicate this. As you can see, from 10 to 1,800 seconds. We go ahead to insert another expression. So go to lithium-ion batteries, go to particle interpolations, and this one is the particle insertion. Go to insertion particle concentration. That is what we select for this. So you can actually go ahead and select, type this at the expression. It will actually give you the same, it will console will detect that same expression. How about we change the coloring and style? Right, we make it dashed to see how it looks. As you can see, the dashed. How about we change the color and make it a bit this way. So you can actually decide to change the coloring and style depending on which will make your work look quite appealing or make you better explain your results well, or differentiate each result from the other. You can go on, change different colors. Can even make it dotted, make it dash dot, and make it circle, solid. So we want to go to our parameters and add this one variable, which we'll call C. The value will be 1, and we'll name it as the C rate factor for the parametric study. And we go to our definitions as well. Maybe we have to define it in our definitions as well. This what it actually means, or what console should actually do with it. And we'll name it as the discharge current for the parametric We've actually added one variable to our variables and a variable to our parameters to help explain, to help us continue the next work we are about to do. Because if we do not define these parameters, we will not be able to do this. So we'll move to our definitions, and I want us to add another function that will be non-coupling, which will be integration. Select a boundary, which will be at the end of this. So we choose boundary 4, and we want to change the operator name to positive CC. As we can see over here, change it to positive CC. And we'll move to the electrode current density, and we want to duplicate it. So we have a second one over here. And I want to change the name to, or just include steady. Yeah, steady. So it's, and I want to change the inward electrode current density as well. Like this. Want to make this steady one. We want to move to the solver equations, configurations. Before that, let's add a steady, a new steady to this work. And I want us to look at a time dependent with initialization. So we double click on it to add it, and we close the side. So we've added another steady, and we chose a time dependent with initialization. So we move to our time dependent, and we change our range 0, 4, to the seconds. So we choose our times from 0 to, we choose 40000 for 40,000 seconds. So I would like us to modify, click on modify model configurations for our steady setup. And we will over here we'll disable one of the electrode current density, which is 31. So it's either you click here to disable, or you can actually right click to disable. When you disable, it should appear like this, as you can see. Go to time dependent, and we'll modify as well. We go to the current density, where we will disable 32. So for the second steady, what we did was we disabled steady 1, and for the first steady, we disabled steady 2. So I want us to add a parametric sweep, where we will vary this is what we vary. So I want us to choose these values, 1, 2, 4, for parametric sweep. These are the parameter value list that we'll actually use. Move to 32, time dependent, times 0. So we want to show our default solver for the parametric for the stage 2. We're going to add our default solver for steady 2. So for the time dependent solver 1, we want to add a stop condition. This, as when you go to solve solution 3, click on it, it will open several options, and you click on the time dependent solver. You want to add a stop condition to our steady 2. I hope you're all following me. So we click on add over here. We click on this button, take it to the add. Then we're going to input our expression, stop expression, that we want console to check for us. That when he sees this, it should actually stop for us. Compound. This is our stop expression. So we also want the output to be steps before and after stop. That's what we want console to show for us. And we want to click this add one and check over here, uncheck it. I hope you're all following me on this up to this point. We'll go to study 2, parametric time dependence. Look at our times. So you can actually check it from 0 to 4,000, 40,000. Click here, node group, time stored in output as well. And before that, let's go to a time dependent solver and check as well. Look at our output times. And we want it to be steps taken by the solver. So I hope you're following me to this stage, up to this point. Okay, so you move to study 2 again. I want to uncheck this generate default plots. Afterwards, we want to compute and see our results. So as you can see, our computation starts running, simulation starts running. You see our results. So if you followed me to this stage, you should get this result. So we want to go to results and add a 1D plot group. Want to plot some of the results based on the information, the computation that we just did, which is we'll use the data set from study 2 solution 3. That's study 2 solver 3. And we have study 2 solver 5 too as well. Parametric solution study 2 solver 5 as well. So this solver 5 is from the study 2. Stop condition that we added and everything. So we go ahead to add the parametric study 2 parametric solutions 1 solver 5. That is what we'll add. We want to add a point graph to this. And I want to select till the end of this as we choose domain 4 for this. And also we change this to this. So automatically change to electric potential. If we plot, you should have this result after plotting. Go to the parameter. Choose expression. And we choose so okay, so oh, sorry. I think I shouldn't have added this to this. And it plots like this. We want to show legends. Do manual, we show legends. How about we change this to 0.1? See, see, this goes to 2C. Sorry, 2C, and this goes to 4C. As you can see. Go to the title. We actually choose manual, discharge curve, curves. We plot. So this our electric potential against discharge curves, but we are not done yet. We change this. Meter. It's actually capacity. So this is our voltage. Yes. So we want to edit the manual axis, which is here 20. We want to see how it look like. Okay. How about we make here 2, make here 4.4. So this is how it should look like. How about, so we actually plotted our discharge curves, our voltage against capacity. Being able to, using a 1D, being able to draw a discharge curve. And you can actually see we should go here, piecewise. You see how piecewise? If we go to parametric sweep, seeing all our plots, as you can see. So before, and I think there's one part here I have to, this is voltage. Yeah, so that was the last part. And thank you all for following up to this part, and I hope you'll be able to make these plots and get these results. Thank you.